Hey guys, it's Coach Scott again. Here we go, here with another edition of Problems for Germantown Red Devil Chemist. Alright, so let's look at 4G problem 2. Alright, and this is your basic empirical formula problem. Most of y'all can knock these out in your sleep, but let's work on some. So let's see the problem. Use the following data to calculate the empirical and the molecular formula for compound R. We don't know what it has, but we do have the composition by mass. We got potassium 35.56%. We've got iron 17.02%. We have carbon at 21.88%, and we have nitrogen at 25.53%. It also says it has a molar mass of 329 grams per mole. We might need that later on. So first, let's set us up a table, or let's make an assumption. If we add all this up, guess what our mass is? 100%. So if we were to make an assumption that we have a 100 gram sample, then potassium would have a mass of 35.56. See where we're going with that? So what we're trying to do is we're going to have to convert these masses of the sample, into moles, right? Then we're going to take the moles that were in the sample, divide through by the smallest one to make it a whole number. Then we're going to divide everything else by that, and hopefully we'll get some whole numbers. So let's go ahead and create our table. So I've got potassium, I've got iron, I've got carbon, and I have nitrogen. Okay. Columns. All right, so I have 35.56. We're going to call those grams. All right, I've got 17.02 grams. I've got 21.88 grams of carbon. Then I have 25.53 grams of nitrogen. So now we're going to write our molar masses, our gram atomic weights, if you would, of potassium. If you look on your periodic tables, potassium K is 39.1. So rather than 10 grams, I'm just going to fill them in. Okay, iron is 55.85 grams per mole. We'll say grams per mole on all this. We'll call that grams. All right, and then we have 12.00011 grams per mole for carbon. Then we have 14.007 grams per mole for nitrogen. Now, if we divide grams per mole, that's going to give us moles. All right, and I came up with 0.909 mole in the sample, 0.305 moles of iron, all right, 1.822 moles of carbon, and then 1.822 moles of nitrogen. So you can readily see that the smallest number of moles is for the iron. So now if we go through and we divide everything, we'll start with this one, by the smallest number. We could even put a column in there if we wanted to, 0.305, because that's going to make that a 1. All right. If we divide something by itself, it's going to be 1. There's a math property by that name, but I can't remember it right now. 0.305. We got to do everything by that. 0.305. So this is what I got. If I divided that by that, I get about 3. Enough where I can round up. I've got 6 carbon, and then I've got 6 nitrogen. So now I can write my empirical formula. All right. So I'm going to start with the potassium. Potassium has 3. Okay, 3. I can say Fe. Okay, and then I have a CN66. Okay. Now, I need to find out, that's the empirical formula. All right, that's the lowest common empirical Empirical formula. All right, if I get a molar mass of all these, so I got 3 times 39.1 plus 1 times 55.85 plus 6 times 12.011 plus 6 times 14.007. I've already done it. I come up with 329.26 grams per mole. Okay. So the molar mass is 329. That means somebody checked it out, and that's how much it weighed. So if I divide 329 by 329, I don't get a factor. I get a factor of 1. So if I multiply everything by 1, it stays the same. So this is the empirical formula and the molecular formula. So that problem is, can we say, solved? Yes. So now let's look at our second problem. And this is our third problem, rather. This is a hydration problem, a hydrated salt problem. All right. And I think most of you are getting these pretty good too, because it's essentially what we just did. All right. So what do we mean by the term heating to constant mass? That's where you heat that sample and you keep heating it until there is a color change or there is no more weight loss, which means what? It means that you have heated away, evaporated away all the crystallized water, the water part of that sample. And so now it's just sample, okay? And what do we mean by the term dehydrated? That means all the water is driven off. So if you keep heating it until the mass does not change, there's no more water. So you may have to heat it a couple of times, but once that mass stays the same, you're done. You've driven off all the water. So now we're going to calculate the number of waters we have in this copper sulfate salt. Let's read what it says. Copper forms a hydrated salt with the formula CuSO4 with X number of waters. They weigh out a sample of 24,950 grams. That's a lot of sample, right? 24 kilograms. Okay, the hydrated salt, and he heats it to a constant mass. That means it stays the same. So the final mass is what? 15950 grams. 15950 grams. So let's just go ahead and write down what this is. So this is the CuSO4 and the X water. Okay, after we've driven off all the water, what have we got? Just CuSO4. That's all we've got now. So we have a mass for that. Now if we subtract CuSO4 from the CuSO4 and water, we get a mass of 9,000 grams. So what is that going to be? That's going to be the mass of the waters. The mass of the waters. So now we need to figure out how many moles of copper sulfate we have. All right. So that is the amount of copper sulfate. That's only copper sulfate, not the hydrated copper sulfate. It's copper sulfate. Okay. And we have 15,950 grams of CuSO4. Okay. And we need to get the number of moles. And the way we do that, like we do everything with moles, is we take the atomic mass, the gram molecular weight, whatever you want to call it. All right. And if I add in the mass of 1 copper, which is 63.55 grams, plus the mass of 1 sulfur, 32.06, plus 4 oxygens, 4 times 16, I come up with a molecular mass, or molar mass, gram molecular weight of 159.61 grams CuSO4. And if I divide that total by the molecular, or the molar mass, or the gram molecular weight, I got 99.9 moles. Almost 100 moles. In fact, it probably is really 100 moles. Now, if I need to know how many moles of water I've got. So I have 9,000 grams of water that I drove off. That's a lot of water. So let's do our math on it. Change pens. Let's go to a fat one. We'll do purple. So I have 9,000 grams of H2O. The gram molecular weight of water is 1 mole H2O is 18.015 grams. Some of y'all might be memorizing that. I don't know. We do enough with the water. So if we multiply that, all right, or divide that, multiply 9,000 by 1/18, or divide 9,000 by 18.015, either one works. We come up with, let's see, 499.6 moles of water. Go ahead and put CuSO4 here. So you see there is more moles of CuSO4. All right, and if you really, let's go ahead and do a rounding. So that's really 100 moles, and that's really 500 moles. So now I've got, for every 1 mole of copper sulfate, how many moles of water do I have? For every 1 mole, I've got 5 moles of water. So my answer for there would be CuSO4. We'll write the formula out with 5 moles, 5 waters complex with it. Or if you want to get technical, the X is equal to 5. That's that problem. We're done with that one, so we've got 3 of these problems out of the way. The next one is a real long one, and we'll get that knocked out tonight also. All right, so I'm going to go ahead and sign out now. So let's go, Scott, saying out, and see you guys later. Bye.